constant times L1 minus L, that is 200 Newton per meter times 0.2 meter, that is 40 Newton. OK， 大家看到了？所以这是力的分析的一个部分。And then now, how are you? What was asked? Okay, you are asked to find the free body kinetic diagram. Okay, yeah, this is just the starting. What are the free body force kinetic diagram? Okay, the thing is subjected to a weight mg. Okay, it could happen also. You'll be subjected to, yeah, because you are being pulled, there is a pulling force P. And then next, you'll be subjected to friction force F. Okay? In case there is no friction, then you can write the issue. 好，看到没有？所以你那个力，现在已经。你如果要去写你的运动方程，你就把所有的力写下来。然后我们刚才还少了一个力，就是你的正向力。你的正向力。So you can start writing the equation in the y direction. Y upward positive. Is the force in the x direction, rightward positive. Okay. So with this, then you are able to write the equation n minus fx cosine theta minus mg equal to m0 for the block not jumping, and then friction for the pulling force. Okay, yeah, minus the spring force. Okay, to make the equation more distinct, I will replace this by the pulling force. Yeah, otherwise sometimes it's quite confusing. So many F. Yeah. So this will make the two distinct. Yep. P for the pull. Okay. So with this, after symbolic return, substitute the value, get the answer. So this is a practice I recommend you. Write the symbolic equation when you first draw it. There is no hurry to substitute any value until you have already re-expressed the expressions. Okay? 所以你们练习最好你要用这个保持这个习惯，先写你的符号节，然后反正你学过代数，符号节移过来移过去，把你要找到的先找到，然后最后才能带入数字。你的课本为什么都是一堆数字节啊？因为那是写给美国学生，那美国学生数学没有比你好，人家都一堆数。那你如果说你符号节可以处理，你先把符号节接完。好 ，Then next we come to the example of the this pulley motion, cable tension. So we already talked about the spring. Another extension of the spring is what we call inextensible cable. Inextensible cable is so rigid that it doesn't extend, but if it's thin, it can flex. Okay, so this is commonly used for in your pulley. The cable together with pulley can help you increase the mechanical advantage. So take for example of this compound pulley. In this compound pulley, you have a fixed pulley on top to change the direction of the cable pull. And next, you have a movable pulley at the bottom to increase the number of the pulling force acting against the weight. So in this case, how do you obtain the equation of motion? OK， 你看图的话也是一样。这个图看了，哎，大概可能你不太明白，那你最好还是要画出来。还是要一再强调，动力学是一门几何的课。你如果不画出来的话，你的力是搞不清楚。比如说你动。Okay, here's the question. How much is the pull to lift up a weight? Let's say I draw. How much is the pull force? Okay. If you have to overcome the weight. Okay. How much is that? Okay, this is the fixed pulley. Okay, assuming there is no friction, the cable will perfectly transmit the tension. Okay, this is the first tension. This one, if you make the cut, okay, this will be. This is what you practiced before. And then what are you going to write? You are writing the equation for OK， 你在写牛顿第二定律的时候，前提是什么？你可以在弹簧上写牛顿定律吗？我们来问一个问题，来，我们看看后座同学，哎，我找最后座的，后座的最严厉最好，哎，就你了。牛顿定律可以用在弹簧上吗？哎，最后我以为就你了，对，牛顿定律可以用在弹簧上。牛顿第二定律。如果弹簧没有质量，你可以用吗？Yeah, can you apply Newton's second law to a spring? Yes. But what happens if the spring has no mass? You never know spring can be no mass. Okay, let me show you the video. 那我们来看一下。Let's look at this apple. Okay, I don't have the one with the, yeah. Okay, this is not a spring, but imagine if you have a very light spring or very light string supporting an apple. As compared to apple, does the spring has a mass? Have you ever had a thread for stitching? A thread as compared to apple mass, is it massless? Okay, so in this example, how can you write Newton's law for a thread or for a cable which is very light as compared to the weight? What's to be written? Is it still Newton's law? Newton's second law? Okay. Indeed, it reduces to Newton's first law. Because the right hand side, if the mass is 0, then it should be a static balance. Okay, so that is the fact about the Newton's second law applied to something massless. Okay. So likewise, how do you write the equation for a pulley? In this case, we assume what is the assumption that you are not told? The assumption is the cable are massless. Okay? You don't apply any Newton's second law to the cable. Okay? So that's why you can write this is F equal to ma. You write these to the block consisting of massive weight. And if this is the block, you have to cut them out all from the cable. Cables should not be part of the system if you are drawing the free body force. And this is what you're writing. This force summation is equal to ma. And you have to decide what are the direction of the motion. If you decide the motion to be upward, positive, okay, then the sign is different. Okay? So what are you going to write? You're going to determine, okay, if this is the case, if you write downward positive, then you have the mg minus 2t is equal to ma. Okay? These only apply to the block. Okay? And then next, how do you find the tension? As I mentioned to you, the tension can only be found from the cable. So you can write this force summation equal to ma of the cable. The acceleration of the cable is non-zero. Okay? And then, but because of the mass is zero, okay? Now you are writing going up to be positive, then you have T minus P equal to 0. So in this way, if you do the substitution of second equation to the first equation, then you can find out the pulling force is your mg plus ma divided by mg minus ma divided by 2. Depending on your convention. 好，所以那个公式你要记得 ，OK。那我们特地会拿这个滑轮缆线这个例子来讲，是让你分解。So rather than handling a compound pulley which is complex, I'll start off something which is simple. This is basically a fixed pulley. How do you do the analysis? How much the force is required to push up the block? Okay, the block is supported by the tension. The cable are transmitted fully. Okay, tension reaction is going to be equal to the pull. And then what is acting on the pulley alone? There are supporting force that is going to support both tension. And then next, then supposedly you can also write the equation for the block to be supported by the tension. This is mg minus the T is equal to ma. Okay, and then what's next? And then how about cable? Cable, yeah, if you want to write this as a whole system, you can have normal supporting force, which is in the opposite direction to the pulling force and the tensions. So the two are equal. Okay. And then lastly, if you want to consider whether they got this friction coming from the pulley, you have to it depends on the pulley mass. 所以平常你们解题啊，都跟你讲，滑轮左手边的缆线跟滑轮右手边的缆线，它传动的力是一样的，前提是什么？慢慢的拉，加速度是0。OK。 那还有另外一个情况，什么时候这个缆线的传输力是一样的？那就是你的滑轮超小。So do you remember the KUKA robot or your conveyor belt? If this cable has been used to the robotic arm, and if this robotic arm got to be turning the arm fast, okay, and if the pulley has massive, J pulley that we're going to introduce you later is not zero, then your transmitted force on the left hand side and force on the right hand side of the cable are not equal. Okay, so that's why it's important to go to the detail and write the full equations. State all the assumptions you have. Okay, you should not just do any arbitrary assumptions. Okay, you have to go to the detail. Yeah. So this will be important in the second half. Okay, so with this all assumption, you come to the simple fact. Okay, the weight overcoming the tensions, okay, is causing a downward positive acceleration. Okay, and how much is the acceleration? The acceleration is weight minus the pulling force divided by the mass. Okay, so this is a detailed working step, even though it is elaborated, but I hope you can understand the meaning. Okay, and then, yep, with this, then we concluded this part of the study. So we are studying for kinetic for single particle, but bear in mind, this single particle does not have the shape of a point. We have the shape of a car with 2-wheel, 4-wheel, car body, and passenger. So this kind of simplification of the model is valid if all the passenger, all the wheel are moving at the same speed. Okay. Likewise, for the pulley system, you can ignore the presence of the pulley, assuming the pulley mass is very minor, or assuming the acceleration is very minor. But this kind of assumption is not valid if you have the pulley applied to robotic arm like in the KUKA robots. It's still valid for the lift or elevator, because the lift or elevator will stop every stop. You just accelerate for a short while. Okay? Yeah. Okay, then next. Okay, next we'll move on to the circular motion. Yeah, circular motion is more complex in kinematics. Okay, but the way you write the equation is still the same. Newton's second law are the same. Okay, except you could use different coordinate. Okay, take for example, then we're talking about this pendulum motion. Let me show you the Apple pendulum again before talking about this. Yeah, here's an Apple pendulum. Yeah, the pendulum motions. Yeah, the apple is tracing a circular arc. Okay, from the left to the right, from the left to the right, and then in that case, previously we described you could possibly use the normal tangent coordinate. But normal tangent coordinate is something attached to the moving object. Okay, so you might want to attach your coordinate to the supporting point, which is not moving. In that case, then you're going to use the polar coordinate. Okay. So then you have a pendulum. If it's swinging, you have tangent, you have the normal. Okay? This is one coordinate. you can describe it. But another coordinate that you can describe is the radius and the angle coordinate. This is what you call polar coordinate. And this is what you call your anti-coordinate. Okay? The view is completely different. This view is stationary, but this anti-coordinate keep changing. Your n is pointed vertically and up, and then your n coming here. Yeah. So anti-coordinate is attached to the pendulum. Okay? So this is how you hack. Okay. In case of the pendulum swing, you know the speed, the tangential speed is keep changing. So you see the tangential speed can increase to maximum at the bottom and decrease to 0 at the top. Likewise, this tangential acceleration also the same, but there is also this centripetal acceleration present. So you can see that the acceleration A is going to keep changing. Okay, we'll arrange you to do one test for this to understand this tangential acceleration. So meaning you're going to use your handphone. We arrange the sessions. Yeah, you use your handphone as a pendulum. We're also going to use your hands form for a swing. Okay, not just a one directional swing. You're going to circular swing. Okay, yeah. But there is a disclaimer. Save your camera. Save your handphone. We only provide you a rod, a string. Okay, no guarantee on the safety of your handphone. You have to do with care. Okay. So how do you describe the motion of the pendulum? As I told you before, at the bottommost position, you can describe using x and y coordinate. But this x and y coordinate keep changing. So in the end, this is not really valid. And then you change to anti-coordinate, tangential normal coordinate. Okay. So when do you use this kind of coordinate? You use it when the pendulum is shifted by the horizontal motion. Take for example, you can have a simple accelerometer by installing a pendulum in your car. Okay, if you suddenly accelerate, okay, the pendulum will move together with the car, but it's lagging behind. 好，我们这里再插一下。So imagine this is a car. Okay, and you have a pendulum hang on. Okay. Okay, let me change the direction to tally with if you're now accelerating. This pendulum will be lagging behind. Okay? So this motion, okay, to be precise, I should define this motion as x, the velocity is x dot, the acceleration is equal to x double dot. So in this case, how do you describe the motion? Okay? Because I know that the car is moving with the forward acceleration. So do my mass, isn't it? So do my pendulum. Even though it's swinging back, okay? But in this case, you can see that what is pulling the pendulum? It is T, the cable tension. Okay, this cable is inclined with the horizontal direction by angle theta. So if you now write the equation of motion, because this is the pendulum mass. Okay, force summation Fy is equal to MAY. This is X, this is Y, but because it's not jumping up and down, this is 0. And then next, Fx is summation equal to MAX. This is MA, okay? Non-zero. What is the horizontal force? You're going to have your this T cosine theta, okay? It's going to be equal to MA, okay? Yeah, I still don't know my T. I got the T from my first equation. The first equation is going to be of T sine theta minus the weight equal to 0. So as such, I can find my T is equal to mg divided by sine. Okay. So in that way, your acceleration can be obtained from the angle of inclination. 所以单摆会因为你车子往前加速的时候滞后，就好像你骑机车，突然往前冲，那你身体是不是往后 ？OK， 你有没有想象过？你骑机车。那你突然间往前加速 ，you do not suddenly accelerate. So, how is your orientation of your torso? OK? 那你上半身的姿态是什么？你上半身就往后仰啊，对不对？那你上半身往后仰是为什么？你的躯干是被拉动，有一个张力拉力，然后这个拉力有一个水平分量，提供你向前加速。OK， 所以我们撇开你相对运动，我们单纯就看你的躯干向前倾、向后倾，就跟单摆的这个分析是一样的。OK， 你的躯干向后倾，实际上你是被拉着向前。Okay, and then next. Okay, we have been using x coordinate, anti coordinate, and we could even using the polar coordinate to describe the pendulum motion. But the use of pendulum motion, the use of polar coordinate for pendulum motion is not much different from your anti coordinate. Okay, except the case when your pendulum is elastic and that can be extensible. So let's watch a video. Okay, how do you write the equations if you are using the polar coordinate? You can describe the radial acceleration is equal to the mass times radial acceleration minus the centripetal acceleration. And then the circumferential force is causing the circumferential acceleration. That consists of two parts. The first part is the angular acceleration times radius, and the second part is what you call the Coriolis effect. We have obtained the Coriolis effect before. Okay, so let's watch a video showing you a strain case where you can have the autoparametric resonance.
If you get this mass just right, and then I get this string just right, something weird happens. It bobs up and down, and then it stops bobbing up and down and starts being a pendulum. And then it stops being a pendulum and starts bobbing up and down. It goes back and forth between bobbing up and down and being a pendulum. This is called autoparametric resonance. It's where the energy from the spring is transferred to the energy of the pendulum, and then the energy of the pendulum is transferred back to the spring. If you get
So now, rather than looking into that complex mode change between spring extension and the pendulum swing. We now just simply focus on something simple. First is the circular motions. Okay, so circular motion, you know that to describe it, the object is tracing a arc, then the speed is equal to the arc length divided by the time. Okay, and then for the hammer throw, okay, the sportman got to provide the pulling force as a centripetal acceleration force. Once it let go, then the hammer will be thrown away along the tangent line. Okay, how much is the centripetal force required? As we tell you before, the centripetal force is the force required to change the direction of the tangent line. So this change of the, imagine the tangent speed are going to change at point A and point B. The change in the direction will be delta V, and this delta V is then obtained as the tangential speed times the small angle change, and then divided by time. Then in the end you obtain mv squared over r. Okay, it could be tested. So ask you to draw in the midterm. So how do you get the tangential acceleration? We might not ask you to calculate the number. We might ask you to do the drawing. Okay, so bear in mind how to draw. Okay. So and then next, before throwing the hammer, you have to spin the hammers, and in that case, you require a tangential force to do the speeding up of the tangential speed, and then at the same time, you need the centripetal force to keep the centripetal acceleration. That is to change the direction of the hammers. Okay. So as a result, you can see that the tangential force requirement is not tangent to the arc length. Likewise, the acceleration, total acceleration, is not tangent to the arc length, but it has a centripetal component. Okay? And then next, likewise, just now we are talking about planar spin. If you're now doing the spin horizontally, you also need to maintain this centripetal force. Okay? And in the next example, we are looking at the vertical spin. This vertical spin is to spin the bucket of water, and then how much is the speed so that the bucket of water don't hold out. Okay, let's watch a video.
Good morning. Today we are going to determine the minimum angular speed to spin a bucket in a vertical circle such that water will stay in the bucket.
Living physics.
Didn't we do this already?
Yep, twice.
Actually, no. We have determined why water stays in the bucket and analyzed the situation generally. However, we have not solved this particular problem. Billy, could you please read the problem, and Bobby, could you please translate?
What is the minimum angular speed necessary to keep water in a vertically revolving bucket? The rope radius is 0.77 meters.
Minimum angular speed equals question mark, and radius equals 0.77 meters. Bo, please solve the problem.
I got nothing.
Don't look at me.
We need to draw a free body diagram.
Sure, but where do we pause the bucket to draw the free body diagram?
Okay, let's start by spinning the bucket and slowing the angular speed down to the moment where water just barely starts to flow out of the bucket. You can see that's right where we're talking about. Bobby, where is the bucket physically located when water just starts to flow out of the bucket? Well, it looks like water starts to flow out of the bucket when the bucket is near the top of the circle. That is correct. Realize water is most likely to flow out of the bucket when the bucket is at the top of the circle. So, Bo, please draw a free body diagram of all the forces acting on the bucket when the bucket is at the top of the circle.
Okay, so
Force
we stop here, then we straight away go to the equation so that you can see the answer. Okay, how do you write the equation? Okay, you are writing it based on the free body force diagram. Imagine if the bucket is at the top, it might still providing a cable tension, but on top of the cable tension, there is this weight of the water. Okay. On the other hand, if the bucket is at the bottom, the cable is opposite to the weight of the water, and in the horizontal directions, the cable tension is perpendicular to the weight of the water. So let's see, at the bottommost position, tension overcoming the weight is providing you the centripetal force. So your cable tension is going to be mv squared over r plus the weight. Okay, at the topmost, how much is the tension? Okay, the tensions plus the weight is going to be mv squared over r. Okay, so in this case, you can see that you need a minimum speed to overcome the weight so that your cable tension is positive. Okay, so if you happen that your cable tension suddenly become 0, that is going to be the weight that is providing you the centripetal accelerations. Okay, so in this example, you'll be able to determine the minimum speed. That is v equal to square root of rg. Okay, it might be quite a abstract physical experiment, but now we put this equation to the real life. What is the maximum speed for walking? Did you ever ask this question? So it bears similarity here. Okay, let me show you. Okay. 好，我们稍微讲一下。Okay, let's make a quick guess. What is the maximum speed of walking? 来，有同学参加竞走的吗 ？Do you have a race walking? 有吗？学校运动会有竞走吗？那我就先问你，走路跟跑步有什么不同？ So what is the difference between running and walking? Okay, for walking, you must have one leg always contact with the ground. Okay, and how about running? You have certain moments both legs above the ground. Okay, so now next come to the question: how do you predict the maximum limit of your walking speed? Okay, let's see. Yes. Okay, you can model the man as the walking with a constant radius. What is a constant radius? You are inverted pendulum. Okay, you walk with your leg fixed in length, and with your gravity moving up and down along the circular arc. Okay? And the tangential speed is your forward speed v. Okay? As you are moving forward with increasing speed, yeah, you may not know that your body center is subjected to centrifugal force. Okay? Without the weight being the centripetal force to keep your body down to earth, your gravity center will go off. So as a result, you can see that your maximum moving speed must be equal to must be obtained from the condition that centripetal force must be less than the weight. And this centripetal force, this condition happens when the forward tangential velocity is less than the square root of g over l. Okay? So, yeah. So did you ever ask why the astronaut going to the moon keep jumping? Can't he walk? 太空人，哪一个是第一个上月球的？是 Armstrong 还是什么 啊，然后为什么上了月球他插国旗不能正儿八经的走路啊？啊，他想走都每一步他的反作用力太大了，他一踏步他就弹起来 ，OK， 所以它的原因是什么？你的前进速度，还有你的离心力 ，OK， so with this then we can quickly summarize this century, yeah. Okay, and then and then next experiment we're going to do is this conical pendulum. So today we have run out of time. I'm not going deep into that, but we'll spend time doing some experiment like this. Okay, and then the other part that you can look into is the Bangtan. Okay, it's something also common. And last part is this trebuchet throw. Okay, using the polar coordinate. Okay, with this then I'm done for today. Thank you for your attention.